Okay, why don't we go ahead and get started? Today we're very lucky to have Diane Karakla here today to give us a talk about planning MOS spectroscopy with the NIRSpec microshutter array. This is both a talk and also a demo. Diane is a member of the STScI NIRSpec team, and she's our resident expert on MSA planning. So take it away, Diane.
Thank you, Christine. Welcome, everybody. Thanks for joining. This is, if you're wondering what this one's all about, I'm going to be going over some slides to introduce you to the MSA planning tool for planning MOS spectroscopy with NIRSpec. And after that, I'm going to give a live demo. And I wanted to point out that there are materials that you can use to follow along with if you already have APT downloaded. If you don't, you can go to apt.stsci.edu and download the latest version of APT and follow along with the demo later on in the talk if you'd like. There is a catalog that I've provided users, and those have been attached to Christine's email about the lecture today, and some step-by-step instructions in case you get lost as well. And
they'll also be posted on the web page for Diane's talk after the talk.
Very good, yeah. I wanted to point out this is a joint effort of many people over the years. I'm probably Tracy and I are probably the people that have continued through this effort for the whole entire time. So we both know a lot about the tool. But Gary Curtis is our main developer. Carrie Gilbert has helped in the past. Tracy, of course, Jeff Valenti, Susan Casson, and several others have helped. These are the primary contributors to this work. And Klaus is the original concept for the tool came from Klaus, and he developed an IDL prototype for the tool that I'm going to be discussing. Okay, so the first thing I want to talk about is, actually I want to go back to my outline. I don't know what happened to it. Here it is. So this is an outline of my talk today. I'm going to be talking about a timeline for MOS observations, proposing MOS observations. I want to talk a little bit about target acquisition and pre-imaging considerations. This is something that you need to think about in advance. There are MOS observation planning challenges, which we've tried to handle using the tool that we've developed for you. But I'm going to talk about those challenges. And then I'm going to talk about key planning parameters and strategies that you can, change or manipulate in the tool. And there are the key planning outputs that you'll receive from using the tool. And then finally, I'm going to give the live demo of the tool. But first, I want to talk about all these other things. So a timeline for MOS observations. I want to say that there are really two main phases at which you will be preparing programs using the MOS tool. The initial submission more or less requires you to use this tool. And the reason is that you get a much better understanding in order to estimate your time that you're requesting, including the overheads that you need to see what the visit structure is going to be. And the visit structure is very much going to depend on what type of plan parameters you use. So it's going to depend on, in particular, these key things: the number of observable targets that you derive from using the tool, the number of MSA configurations needed to complete your observations, all your Dithers exposures, and then, again, how many visits that you'll be getting in the end. It will largely determine the amount of time you need to ask for. So there's the initial proposal submission phase that I've shown on the timeline here. And then once that happens, the TAC will decide on who is awarded time. There is a long-range plan that's developed from those successful observations. A fixed orient is assigned to those programs that are MOS observing programs need a fixed orient in order to proceed, because detailed programs cannot be developed until the orient is assigned. And if near-cam pre-imaging is required to not only identify targets but reference stars, to plan the observations in these tiny little micro shutters, you have to be exactly sure where they fall into the shutters in order to plan little slitlets on them in the sky. So if you need to be precise about your pointing for your science, you'll need near-cam pre-imaging or other pre-imaging in addition to the fixed orient assignment. And then finally, the second phase is program submission, and you'll be preparing your detailed program submission using this MOS observing tool. And so this tool will then provide potential targets, suitable reference stars, and then accurate positions for both of those, and the MSA configurations that you need to do your observations. Okay, so let's talk a little bit about some observing considerations about accuracy. So the way the tool works is it operates with an input catalog. The catalog relative astrometric accuracy, as you can see in the third column of this chart here, if you have near-cam imaging, for example, you'll be able to get a relative astrometric accuracy of about 5 milliarc seconds, which will provide a delivered pointing accuracy with our TA methodology that we provide of 20 milliarc seconds, or about a tenth of a shutter, MSA shutter width. And so there are really a couple of different regimes here for what we call MSA target acquisition using reference stars. And there are 5 to 20 reference stars that need to be defined for each visit. The two regimes are an optimal TA or a relaxed TA. So some science doesn't demand this type of pointing accuracy with the shutters and the sources and the shutters. And that is for like extended sources or sources that don't require the flux accuracy that's needed. And so you can actually plan your observations from other types of images like HST images, and even with HST imaging you can get down to about 5 milliarc seconds with careful planning. But typically that I would say an individual HST mosaic might be in the range of 10 to 15 milliarc seconds. And I'm going to use a catalog today and assign a 10 milliarc second relative astrometric accuracy there. So we're going to be in the optimal regime, but sort of at the far end of the optimal regime. And then alternatively, there is verify only, which is just point and shoot. There is no target acquisition, but it allows people to do science with the MSA with MOS mode, and it's targeted for limited science cases, extended objects, etc., or in fact maybe even planetary work. In that case, you can hope to acquire about 100. I think there was talk that we can do a little bit better than that, but 100 milliarc seconds or maybe even 60 milliarc seconds in arc minute. Okay, so one of the first things that you have to decide is whether or not you need this near-cam pre-imaging in order to derive this type of accuracy for your catalog. And I also want to point out that the pre-imaging that you do use, if it's HST pre-imaging, you really need to have an area of about, well, minimally, the size of the MSA is about 3.5 arc minutes squared, but you want to have a little bit more than that in order to identify reference stars that can be utilized in order to really optimize your pointing. Okay, so this is just a picture of the target acquisition era versus the catalog astrometry. It's basically showing you a picture of what I just spoke about. So if the different curves represent different numbers of reference stars. So you can see that the more reference stars you have, the improved accuracy, you get improved accuracy with that. This figure is from Tracy Beck, her SPY article. I wanted to point out that so TA proceeds with at minimum 5 reference stars, and you can see as a function of the astrometric accuracy on the x-axis there, you need about at least 15 milliarc seconds to be in the regime of optimal TA. Okay, so there are a number of planning challenges with the MSA. First of all, I'm showing you an idealized MSA figure over here, 4 quadrants. Each quadrant has 365 by 171 shutters. They're rectangular. You can see a little picture up in the upper right. They're rectangular little doors that open, and they can be configured independently of one another by electrostatic charges that are applied. And there, you can see relative to those 4 quadrants of the MSA, you can see where the fixed slits in the IFU aperture are in this picture. And then I would also point out that this picture that I'm showing is mapped out onto the detector array. Those 2 red squares that you see are just a projection of where the detector array, where the quadrants fall with respect to the detector array. I'll point out that there is a gap of about 20 arc seconds between the two detector arrays. So when the spectra are dispersed across the arrays, there will be a wavelength gap for any given pointing that's derived. So that's why we always advise people to dither their observations. And if they want to recover all of the wavelengths, they have to have at least 2 pointings dithered by about 20 arc seconds. There are optical distortions and velocity aberrations that must be taken into account for getting precise positions correct of the sources relative to one another. The velocity aberrations depend on where the targets are in the sky relative to the direction of movement of the telescope. This is a picture of the real quadrants showing all of the failed shutters. The failed shutters occurred for a number of different reasons. Just whenever you're dealing with a real device like that, there are going to be some percentage of them are going to be failed shutters that fail to open. Those are the failed stuck shutters that you see in black. In addition to that, there are failed open shutters, and those can cause contamination of background, with whatever's being exposed in the background on top of a target shutter. So you have to plan around the rows that are affected by that, by those open shutters. You want, as I mentioned before, you want to dither to cover the gaps. So you have to be able to describe or prescribe dithers to this tool and be able to follow the sources through the dithers. You want to observe as many sources as possible at all dithers. So that was the goal of our tool. The solution is to use the planning tool, the MSA planning tool, MPT for short. And you can download it from this location here. And this will deliver optimal pointings and MSA configurations for you. Okay, so key planning parameters. Let's talk first about the catalog and about target weights. So a source catalog is always necessary for input to the MSA planning tool. Well, not always. There are certain cases, limited cases, that don't need to use a catalog. We're working on those, though. Let's see. So the catalog can have a column of target weights, and those weights should be integer values. And the way it works is that a weight of 100 is equal to 100 times a weight of 1. So it's very straightforward. The relative weighting is very straightforward, and you should interpret it as very straightforward. Let's see. You would also like to order your input catalog by target weight before you ingest it into the tool. This actually helps get the most desirable sources into your MSA configurations. The next thing you'll do is derive a primary candidate set and a filler candidate set in order to work with to create plans. And I will point out that only the weights of the primaries are used during planning. The filler weights are not used, but if you've ordered your list by weight and the fillers are weighted, then you should preferentially derive configurations that include the most preferred fillers as well. Let's see. So the best pointing will be derived by the tool for you from the weighted primaries. And the fillers will actually help to optimize the MSA configuration at any given pointing, because you're adding in sources where you would otherwise not be observing. So you would not be observing or utilizing the real estate that's there and available to you if you weren't using the fillers. But if you do want extra observations of your primaries, it's a nice thing to keep in mind that you should include them in your fillers list as well. And in that case, you would get extra observations of those primaries for free. But if, on the other hand, your preference is to observe as many fillers as possible in the extra real estate that you have in the MSA configuration, then you can leave them out of your filler list. Okay, so this is what target weights does. When I've created a plan, I'm looking at the plan results from one of the plans that I've planned, okay, that I've made. There I've highlighted, in this particular example, I've highlighted in blue several exposures from the plan, and I'm just looking at the list of targets that were observed in those exposures. And you can see that those with a weight of 300, which is my highest weight in the catalog, were observed. Many more of those were observed than those with smaller weights. So I just want to point out how that works. Okay, another planning parameter is the slit shape. You have to define a default slit shape in the tool. It can be 1, 2, 3, or 5 shutters. And in the 5 shutter case, you can actually have 3 open shutters, or just all 5 can be open shutters. And for every open shutter in any slit shape that you choose, you can obtain nodded exposures. You can have the telescope nod slightly to place the target in the different open shutters. So in the 5 shutter case, you can actually obtain either 3 shutters or 3 exposures or 5 exposures. But the rest of the slitlets, 1, 2, and 3, give, if you choose to nod in the slit, will give you exactly that number of exposures. Okay, so I also want to talk about the shutter margin for a minute. So there's a way to constrain the centering of any targets that are accepted in your final program. You can constrain the centering of those targets to be at different levels, at different constraints inside a given shutter. What I'm showing on the left-hand side is a virtual shutter, and then the dots represent the target centering, where the targets fall in their particular shutters. Now, as you know, since we have a fixed grid of a fixed MSA grid of all these tiny shutters, there are bars between the shutters, and you want to make sure that any target that is accepted doesn't fall behind the bar. But because the sky is the way it is, everything's not precisely planned out into little grids, you're going to get target centering that's all over the place for your targets. But like I said, you can use this methodology to constrain the centering of the accepted targets in that plan. And so what actually happens is, if a target is not within the constraint window and it's being considered to be added to the MSA, it will be omitted, and another target that is nearby will be selected if it has a better centering constraint, if it falls within the centering constraint. Okay, so there are 5 or 6 different levels of centering constraint that you can use, and these are pictured here on the left. And so the result is, as a function of wavelength, you can see what the estimated throughput is as a function of wavelength for the different choices of the centering constraint. So it peaks at around, 1.5 microns, it looks like, and it falls off differently for the different constrained values. And I wanted to point out that in order to use this constraint methodology, you have to have precise positions in your catalog better than 15 milliarc seconds in order to be able to use this. Okay, another planning parameter that we have is Monte Carlo optimization of the MSA configuration. And what that means is that at each step, when I'm considering what sources to add into the MSA configuration, I can choose to just go down the ordered list and try one source after the other in the ordered list. Or I can, in addition to that, I can select that I want to do this Monte Carlo shuffling, and it will shuffle the primary source list and try different orders of sources. So on the left, I've shown an example of how if I go in the order listed there, 1, 2, 3, 4, 5, I can only fit targets 1 and target 3 on there without covering the real estate needed by slitlets that already exist in the MSA. This is just a small blow-up view of a section of the MSA. However, if I tried a different order with the same sources, I can actually fit 3 targets into that same real estate. So the ordering of the primary candidate list can be shuffled in order to more optimally configure the MSA. And that happens at each dither step. Okay, I wanted to point out also that there are 2 different types of algorithms that are used. There's one for dithering. One is called fixed dithering, and the other is flexible dithering. Fixed dithering simply translates a set of shutters to another place on the MSA, and so it's a fixed dither in the sense that they're prescribed by the users exactly. I want to go down, 4 spaces and over 2, and that dither specification can be made into the tool. And so that's a very precise way of dithering. However, because of optical distortions, only small dither, this only works for small dithers, because if you imagine that, if you move by quite a large amount, the relative positions of those sources could change enough that some of the sources may not fall in the slitlet area that you've prescribed for them. So this is a methodology that's very straightforward, but it's only suited to small dithers. However, it's actually more, well, let me talk about flexible dithers first, and then I'll go back and talk about both together. Flexible dithers is dithering by setting user constraints on separations between dither points. So the user specifies separations, or minimum or maximum separations between dither points. And that can be either in the spectral or the spatial direction. And then this method actually handles the relative distortions between the dithers. So larger dithers in this case are fine to use. You can use anything. You want to keep in mind that at some point, you dither far enough, you're not going to get the same sources in the dithered point. So you have to keep that in mind. But at each grid point, the MSA configuration is built and the sources are tallied, and this can also be optimized with the Monte Carlo shuffling that I just described in the previous slide. And then what happens is families of possible solutions are built up from these constraints. It turns out that we not only look at the most optimal pointing at each dither point, but we look 5 down, 5 deep. So at each dither point, there are 5 different pointings that are considered. So we build up this exponential list of families containing the number of dither points that you want. So if there would be families containing 2 members if you have 2 dither points. And then and it increases exponentially if you increase the number of dither points. But then you have this set of families, you never see this. This is what the code is doing. And then it chooses the best family for you, or one of the best families for you. And the best family is the one that observes the largest number of highly weighted sources over all dithers. So I do want to point out that this methodology is quite different from the previous methodology in that individual sources are not matched from one dither point to the next. That is done at the end when we choose the best family for you. We look to see what is the largest number of highly weighted sources that are observed at all dither points at the end. Okay. So this methodology, if you consider just 2 points, for example, you build your best families, the tool chooses the best family for you. The result may be that since sources are not matched between the 2 dither points, as you go, you may actually wind up with fewer primary sources in this case than you would in the fixed dither case. So there's a different level of success for the flexible dithers. It's done completely differently than the fixed dithers. Oops, I'm sorry that's messed up. I don't know how that happened. What did I want to say here? So basically, I wanted to point out that the output is a set of pointings that are going to be optimized for you, MSA configurations for each of those pointings, and of course the target set that you're observing for that set of pointings are going to be outputs. I wanted to point out there are also practical limits on the ability, the robustness of the tool. Let's put it that way. That the time it takes to compute a plan may depend on the number of sources in your primary list, the number of pointings that you're testing, or the number of dither points that you are prescribing. Okay, so I'm going to show you this live, but there's going to be an area of the tool where you can review plan results. You're able to select the exposures by highlighting them in this area here, and then you can filter plan results in this area here, the second area here. You can filter, that you want to look just at the primary sources or just the filler sources or all of them. And you can say, I want to see all of the sources in one exposure or all of the exposures. So there's different ways of filtering results, and I'll show you that in a little bit. And then the results that you filter are printed for you below, showing you column by column what exposures each target is in. The target ID is on the left side. The target weight there is next to it, and then it tells you how many exposures it's been observed in of those that you selected. And then finally at the bottom, there's a histogram of the results that are presented in that third window there. Okay. There's also other visualizations that APT uses Aladdin, and so we're able to plot sources and shutters onto Aladdin, showing it for any given exposure, showing exactly what you'll be observing. If you have a very nice NIRCam image, you can put that on top of your NIRCam image and visualize what you're actually observing. Okay, these are other tools that we provide. There are different exposure views. On the left side, you can see that we have it's a sketch of the MSA, and the utilization of the MSA is shown in orange. The orange rows are colored because there is a target in that row that's utilizing that row for taking a spectrum. The green targets are primers, the blue targets are fillers, and black are contaminants. We don't get rid of contaminants at this point, so you have to be very careful to watch for those. The right-hand side shows a collapsed shutter view, and it shows for whatever margin that you've used for your centering constraint, shown by that white dashed line. You can see that where your targets fall within that margin. These views they interact with one another. So I have highlighted some sources in magenta there by clicking in one of these views, and it shows up in the other view. Those are the exact same sources in the other view. So I just wanted to point that out. Okay, so I'm going to go right now, I think, to the demo. This is just a couple of slides that I have in here talking about the different inputs that I've discussed with you. And then I want to, just start the demo now. So let me escape. All right, so I should be able to go over here, and I have to do the mirror display thing, don't I? They can't see that, right?
You can see it.
Oh, okay. If everybody can see that, should I?
I think you're okay if that's what you're
Oh, actually, yeah. Well,
but you can't see it.
I can't see it, so I think I'm gonna just click off the mirror display thing. I have to stop sharing first,
Okay.
right?
Yeah.
Hold on a minute. Where's my mouse? Displays, system preferences, and displays, and I need to do mirror displays. I'm going to do that arrangement. Mirror displays. Okay. Okay, tell me if you can see. I'm seeing.
You need to share
I
screen.
need to share screen again, right? So, where's that?
It's on the bottom.
No, yeah. Thank you. Oops. Okay. Hopefully people can see what I'm seeing now. Okay. Let us know if you are having trouble seeing that. Hopefully. I'll blow this up as much as possible. Okay. So in this particular, I've started APT. I've already got a program loaded there just in case I had trouble, but I'm going to start fresh, showing you how to start one up. So from this pull-down menu, you select New JWST Proposal. And then just for playing around, I'm going to not worry about the red X's that you see in the proposal information area. I'm going to go directly to Observations, click New Observation Folder, and immediately I have two views. Observation Summary is what you might see if you're doing this, but you click over to the MSA Planning tool immediately, and then you'll see a view like this. Here I have to choose an aperture position angle. So this is the angle of the MSA on the sky relative to north. And of course, nobody really knows what that should be. And there are only certain feasible angles for each target ecliptic latitude. So what we've done is if you choose a bad one, you will not see the true angle to target updated, and you'll get a red X if you choose a bad one. I happen to know that for the catalog that I'm looking at, I've investigated the feasible angles, and there are tools for this. Bill Blair, in his JWST lecture, went over the tools that you can use to find feasible angles to use here. But for this catalog, I happen to know that 45 degrees works pretty well. So oh, actually I have to, sorry, I'm sorry, I didn't show you how to load a catalog first. So let's go back to the catalogs pane here. I want to import a catalog. I want to say it's the white space separated version, and I'm going to browse my directory to find the catalog. And it is right here. I'm selecting it. And the tool is going to automatically recognize certain column types and present them to me here. So it's recognized the ID, RA, and DEC, and I need to pick up this magnitude here. Oh, sorry, that's a I need to go to this column. This is the one I want to do, magnitude, and then this is the magnitude error, or what unfortunately we've called flux uncertainty. And this is the redshift that I want to use, the ZBPZ. And I'm going to swing over here and see if I've got everything. Yes, so there are magnitudes been recognized, the reference stars, whether they're suitable reference stars have been recognized. I just want to say that we'll provide a script that will allow you to construct the catalog, these extra columns that you need. The last 4 columns in my catalog are particularly for identifying reference stars. I think right now you don't need to worry about this. We'll have movies on how to do this in the future. Okay, I'm going to give my catalog a name, and I'm going to tell it that I want to work with magnitudes from this column, and mag errors from that column, and mags is the unit that I want to work with. So it's reading the rows of the catalog. There's about 10,000 sources in the catalog. It's loaded it, and if I click on or highlight the catalog, I see the data associated with that catalog. I also see a couple of red X's. I want to tell it that this catalog was derived from HST data, and that they were mosaic HST data, so it has a relative astrometry of about 10 milliarc seconds. So I'm going to give it a value of 10. And the other red X I want to point out is that it asks me if I want it. So the way this works is that we needed a way to tie an image that's used, a pre-image that's used, into the archived results, into the archive. So this is the way we've done it. You have to choose whether or not you're going to have whether you have already obtained an image, or whether you will be obtaining it external to this program, say from HST data, or whether it's done in this program as a near-cam observation of this very program, or whether it's not required. And for right now, I'm going to select not required, just to get rid of the red X. Okay, you can see that I've ordered my list so that the highest weighted sources are at the top, and there's an internal scroll bar here I can use. If you expand your window large enough, you should be able to see all of the internal scroll bars that you need access to. Okay, so that's my catalog, and I wanted to find a primary and a filler candidate list. So I'm going to select New Candidate Set, and I get a pop-up window here, and I want to name my new candidate set. What I'm going to do is I'm going to filter by redshift. So I'm going to give it a name. It could be anything. I'm going to say redshifts greater than 5. I'm going to add a filter of redshifts, and I'm going to select a minimum redshift of 5. I click in this box here before I click OK, and then I can make the candidate set at this point, but I'm actually going to filter by another thing as well. I noticed that my catalog has a lot of values of 99 for this magnitude when it doesn't know what the magnitude is, so I'm going to filter those out. I select the magnitude, and I say the faintest one is 98.9. That will get rid of all the bad ones. I click OK. So now I've got 2 items in my filter, and I'm going to make the candidate set. There are 316 sources. When I click on that daughter catalog, or it's really what we're calling the primary candidate set, I can see the data associated with the primary candidate set. A lot of the highly weighted sources are there, of course, because I've weighted by redshift squared, so that helps. And these value of 300s I took the top most distant few hundred sources and I weighted them by 300. Everything else is weighted by redshift squared lower in the catalog, so you can see. Okay, so now I want to go back to the parent catalog and derive a new candidate set. It's going to be for my fillers, and I'm going to choose redshifts greater than 3 for that. I'm going to do the very same thing, redshifts with a minimum redshift of 3. Click OK, and I want to do the magnitude filtering as well. Okay, so now I have a primary and a filler candidate set, and you can see the numbers of sources in each. I click on the candidate set, you can see that it includes a lot of the primaries as well, right? As you might expect. Okay, so now I go to the planner. And again, we're back at the aperture position angle. I've chosen 45 because it turns out the HUDF catalog that I'm using is well matched in size to the MSA itself. It's about 3.5 arcseconds squared. So if I want the most sources, if I want visibility on the most sources, I have to tilt my MSA so that those sources fill the MSA. So I've tilted it to 45 degrees. I'm going to say my primary candidate set is 5, the one with Z greater than 5. And it's taking a little while now because it's actually computing based on the primary list that I've selected. It's computed this true angle to target, which is grayed out. You can't change it. Don't attempt to change it. If you get a red X when you do this, then you have not chosen a feasible angle for that primary candidate set. Okay, I'm going to say that my redshift greater than 3 sources are my fillers. I'm going to use a 3-shutter slitlet. I told you about all the different options you have. I'm going to actually constrain to this mid-level constraint area so that I can improve the slit transmissions of all of my targets. I'm going to also nod in the slitlet, so I should get, and it tells me I should get 3 exposures per configuration in this case because I've nodded. And I'm also going to add a dither, but I'm going to add a flexible dither, and I'm going to click Add Constraints. Every time I add a row to this constraint box here, I've added another dither point. So and you can add multiples. Let's choose the first option. I'm going to dither by about the gap size, 18 arcseconds. So I'm only worried about constraining the dispersion distance. I don't care about the spatial distance. So that's what I'm going to prescribe as my dither separation. So now I'll receive 2 primary dither points, and at each primary dither, I'll have a nod up and down with 3 shutters. So a total of 6 exposures for that target set. Oh, sorry. I'm just trying to scroll down here. Okay, I need to give it the gradings that I'm using for this plan, and I can add as many gradings as I want. So I'm going to do the G140 medium res grading, and I'm going to prescribe 23 groups and 1 integration so that I get roughly 1,000 seconds in my exposure times. Right now, the total photon collect duration is not working. It should be scaling by the number of dither points that I have. But it's not working right now. So I told you you'll get 6 exposures, so you multiply this time by 6 to get the total photon collect duration. Okay, the next thing I have to do is I have to decide. The way this works is there is a search grid that's built on the sky, and at every single point in the grid is a test pointing to consider. And what happens is we're building a optimized MSA configuration at each pointing, and then we're tallying the number of sources at that pointing. And so we're going to investigate every single one of the pointings in the search grid. So I've got to set up this search grid, and right now all the defaults are fine. You can just stick with the defaults. These defaults are based on the primary candidate set that you prescribed. I'm going to probe a little bit finer with 5 arcseconds in my plan because you really have to be careful, because if you prescribe a dither that is smaller than the search step size, of course it will have a hard time finding results. So you want to make sure that these 2 parameters play well together, the dither separations and the step size that you're using. You got to use a smaller step size. Okay, I'm going to use target weights, so it's going to refer to the catalog weights to count sources, and it tells me that I need a multiple of 2 configurations to complete the plan. If I specify just 2, I'll get 1 target set. If I specify 4, I'll get 2 target sets. And likewise, as you go up, if I don't specify anything right now, it will complete it will observe all the primaries in my primary candidate set. But I don't want to do that. It takes a little time to run, and it could be 20 configurations later. So I'm just going to make 2. I'm just going to call this, test plan 1. It's probably better to show you that you should use something that makes sense, so that you can, kind of keep track of what each plan represents. And the game is to try a number of different plans and then choose the best one for your observation. But I will try this. So I'm going to generate the plan. This should take about 20 seconds, 30 seconds to run. And then we'll look at the plan results. It'll automatically put me over into the plan results area to view the results when it's done. Okay, so it's done, and I'm going to scroll to the top, and you can see that I'm actually in this third pane here called Plans. That's the plan review place. You can pull down from this pull-down menu. If you have more than one plan, you'll see them listed in the pull-down menu. You can save and view different plans. You know, once you save. Oh, at this point, it's probably very wise to save your APT program, and then sometimes you'll find that it's not that robust and you may lose some of your work. So you want to save after each plan is made, I think. And before I show you how to create an observation with this button or merge plans, I just want to show you that there are different areas in the plan review area. This first area here is the description of the plan, all the parameters that we entered for the plan. This is a list of the exposures, configuration by configuration and exposure by exposure. You can, as I showed you before, you can highlight one or more of these things. Command A helps to highlight all of them, at least in my laptop here. For any one of the exposures, you can look at the MSA Shutter View by clicking this button, Show, here. So I'm bringing that up, and while that's coming up, I'll just remind you that the primaries are going to be green, the fillers blue, and I remind you that we've also used the weights, and so you can see that this is one of the best pointings that it could find. It's utilizing the area of the MSA very well because this is colored mostly orange. If there were any white rows, those are the rows that are not utilized. These are the green primaries, the blue are the fillers, the black are contaminants. So you can occasionally find a contaminant. This is zoomable by, at least on my laptop, you would use your right scroll button, but on my laptop I can just with two fingers just press and drag up and down. I'm going to show you what the slitlets look like if I can get close enough here. So you can see that the size of the target scales with the zoom, so that you can look finer and finer into the slitlet to see where the target is positioned. And as I mentioned before, there is another alternate view, so let me show you that, and this is the collapsed shutter view showing each of the targets, so that if I highlight targets here, I can look to see, oh, that one doesn't show up. Okay, let me try another one. Well, it should. I don't know why that's not showing up, but anyway, let's try it this way. Okay, so these two windows talk to each other. These two views talk to each other. In addition to that, if you go back to your main window, let me move this off here. Let me filter the target results. Let me highlight all of the exposures, and I want to see what targets, all targets are, any flavor target is in all of the exposures, and it tells you there are 24 targets that are completed through all the dithers in this plan. And these are the 24 targets, and I'm going to highlight them with Command A in this view. And they should be highlighted in this view, but it might take a little while. Yeah, it's not working. I don't know why. That was working this morning, I promise you, and it probably is working for you where you are. But so what should happen is everything that I've highlighted here should show up as magenta in this view. So I apologize that it doesn't seem to be working right now, but that's supposed to happen. And let's see. So you can actually, from this MSA Shutter View, you can actually add shutters to Aladdin. So I'm going to try to do that right now. So it's bringing up the Aladdin window, and it's drawing the little shutters that it sees. So I need to zoom in on this so you can see it. So these are the targets that it's observing, this particular exposure. Let me zoom in on an area of it so that you can see that these are all 3 shutter slitlets that are being constructed. And if you might imagine if you had, in fact, let's go back and load the catalog on the same view so you can see it. I'm going back to the main window, and to get out of this funky view here, you go to Form Editor, and you're back in the MSA Planning tool. I'm going to go back to the catalogs area, and I'm going to select my primaries. I don't know if I can select both. No, I don't think I can. All right, so I'm just going to send the primaries to Aladdin as well. So it's plotting these little source positions within the shutters that it's observing. So I think you can see where the sources are within the little slitlets here. If you had an image in addition while you're planning, this helps to visualize exactly what you're getting, what sources you're getting, and what locations. Again, I'm going back to the main window, clicking the Form Editor, and popping back to the Plans area here. So we can at this point create an observation from this plan. I'm going to click this button so you can see what happens. Oops, what just happened? Oh, it put me into the visit view. So if you want to get back to the MSA Planning tool, you have to go to the observation folder. So there we are there. But what I've done here is I've created a new observation with the same name as the plan. I can pull down that observation and see its visits. So there's one visit to execute that plan, as you might expect. The dithers are not too far apart so that they fit into one visit. In addition to that, if you want to get results of your targets printed out, so this will print out the target IDs in your target set, your locations of those targets, and the shutter positions and the positions within the shutters for those targets. There's a way to do that. You could just go to File. First we have to save the observation. So let me just File, Save. I have to save as, let's call it demo test. All right, and it's an APT file, so I'll let it name itself. Hit save, and when it's saved, it should show up here that it's saved to that name. So now you're ready to do file export, and you can select the MSA target info to be exported. Other things that might be useful for your looking at your observation is the pointing file and the smart accounting results as well. Those things are also useful files to print out. If I click OK, it should tell me where it's putting that file. There should be a pop-up box. Here it is. It's telling me it's exporting to my working area. Okay. Let's see. I want to demonstrate merge plans for you. So let's go back to the planner for a second. I didn't get very elaborate on this first plan, but I wanted to point out that I could potentially have added additional constraints here to get more dither points, for example. I could have added all 3 gratings. By the way, it's remembering the plan parameters from the previous run, which is very useful sometimes. I'm going to add the 235, and I'm going to add, I'm going to do 23 of those and 1. And I'm going to add this, the 395M. So all the medium band gratings I'm going to use in this plan. And I am going to actually plan this with a slightly different step size of 7. And let's see what happens. Same parameters. Now I've got to give it a different name. 2, step 7, generate plan. So as long as you're using candidate sets that are derived from the same catalog, you'll be able to merge plan results. So for example, hold on one second. Okay, so now I'm going to select, I have 2 plans here in the pull-down menu. If I go to the first one and I say click merge plans, it'll tell me which plans are viable plans that I can merge. So I'm going to select both of them and hit OK. Okay, it's created a new plan now, so there should be 3, and then the name gets very long. But you can see that there are 3 plans here. This is the merge plan result here. I can create an observation from that and see that I have now 2 visits. It's broken into 2 visits. So these are the kinds of things that you can do with the tool. And let's see, what else did I want to show you? Let's go back to the MPT in the observation folder level. We're in the plans area. Let's see. Oh, I can show you if you want to do manual editing of a given exposure, you can do that of a given configuration. You can select the configuration, and actually I think you can do it from this window here. Let's do manual editing here. I guess I can't. Okay, so from this window here, I wanted to point out that you can actually save this view if you want as an SVG file, or you can export it to a CSV MSA configuration. So you can save the location of the open shutters by exporting to CSV. Let's see. Okay. What did I want to show you here? I showed you merge plans. Yeah, I wanted to show you manual editing, right? So let's click manual editing. Okay, so what that's done is it popped up this different view, and it's given me access to each of the configurations that were part of my previous plan. So there's 12 configurations here. So I can edit any one of them by double-clicking on this table here, the entry on that table. And it should bring up a view of that configuration. It's taking a little time to work, but maybe I'll double click. Oh, there it is. Okay. Okay. So this is at that fixed pointing. The targets have all turned into these black pluses. It's at that particular pointing. So if you wanted to actually, it is still showing the slitlets that were planned for that configuration. So if you want to augment the configuration by adding slits in the white areas, you can do that at this point. You can just blow it up. You can see that this is only 2 entries long, so you can actually construct, if you know where this, if you move around and find other sources that you want to plan. Let me see if I can do this by zooming out a little bit. It's taking a little time. Sorry. Okay, I'm sorry about that. I'm trying to find a better area where I can hone in on a source. Okay, let's just imagine that this source here was a viable source. I can click these 2 shutters. You can select these 2 shutters just by clicking. I should be able to open these shutters. It's just really slow right now because it's trying to remember a lot of things. So this is me adding a custom slit on an additional source in the MSA in an area that was not otherwise utilized, for example. In addition to that, you can actually specify additional background shutters for background measurements as single shutters that are all over the MSA configuration if you want to do that. And let's see what it says. Yeah, and this is where you would do that. You would specify that you were master background. You would click this box here for master background and then go ahead and apply all the extra little background shutters that you wanted in this view. That's how you would do that. So that's basically about all I wanted to show you this time. I want to point out that we are going to be constructing modular movies showing different components of the MSA planning tool. I know it's a lot to ingest at once. But we're gonna, have these movies that are gonna be training movies that we're gonna provide people on, things like merging plans, or you know, how do you create plans from a given catalog, create, you know, just your primary and filler candidate lists and that sort of thing. So we're going to break it up into modular pieces and create those movies for people. And that's about it, I think. So.
Does anyone in the room over here have any questions for Diane? Okay, if not, let's also open this up to WebEx. Everyone's on mute right now, so if you'd like to ask Diane a question, this is a good opportunity. Go ahead and unmute yourself and ask your question. Well, it doesn't look like anybody has any questions.
Okay, I can show them one more thing that I think might be of use. Let me just click that button down. Let's go to the planner again, and let's click off manual planning for a moment. So this is the traditional automatic view, the view of the automatic MSA planning tool that we showed you in the beginning. I did want to point out one additional thing that a lot of people have asked for is to be able to confine the pointing to a fixed pointing and derive a plan at a fixed pointing. This is something that a lot of people want to do. And to be able, you can actually do that. You can just specify the width as 0 and the height as 0. And then you can actually plan a fixed pointing that way. It will actually, I've tested this, it'll actually work for you. So if you know what a preferential pointing of the MSA, and the pointing that I'm talking about is a reference point at the center of the MSA, the 4 quadrants. And that's about it.
Great. Well, thank you so much, Diane. And then I guess our next lecture is going to be in 2 weeks when Nicole Lewis will tell us about TSO observations. Okay, thanks everybody. Have a great week.